Let me start the recording here. Okay, so we're doing recording now. So, okay, Taylor and Maclaurin series it's one of the most important concepts you're going to learn in mathematics. Pretty much every math class I've taken, let me see, well, most math classes I've taken after Calculus 2 involve these Taylor and Maclaurin series, like differential equations involves it, for instance. All right, so the goal here is we want to be able to find power series for a wide variety of a class of functions. Now, the rational functions from section 8.6, like the law and the log and the arctan and the rational functions, the section 8.6 approach works very nicely for those kinds of functions. But if you have like a sine, if you want a power series for a sine or a power series for a cosine, you're not going to be able to use section 8.6 to help you there. But section 8.7 you can use. So what we do here is we suppose that a function can be represented by a power series. Okay? So the power series is written, in this case, in this form. Okay, so f of x equals c naught plus c1 times x minus a plus c2 times x minus a squared plus c3 times x minus a cubed, and so forth. So the c's are constants, coefficients. The a is some number, And we're assuming that the interval of convergence is such that the absolute value of x minus a is less than some radius r of convergence. So if we could, for a particular function, determine what these coefficients are, c naught, c1, c2, c3, and c4, then we would have our power series for that function. So what they do first is they say, let's let x equals a. Let's put x equals a in this equation. If x equals a, what's going to happen to what's going to happen to the second term, third term, fourth term, fifth term, and so forth? Well, when we put x equals a in, that's right, Robin, a minus a is 0. So that means that f of a would equal c sub 0, that coefficient. And so we have a formula for c naught. So for this very general expansion of the function, we know that c sub 0 has to equal f of a. And a is a value that we would give. Okay, maybe a is 0, maybe a is 2. Okay. The next question is, well, can we figure out what C1 is? Can we figure out what the next coefficient is? C1. Well, okay, let's try something. Let's take the derivative of f, of our function f. Well, that's going to give us then this expression here. Right, so of course, derivative of c1 times x minus a is c1. Derivative of c2 times x minus a squared is c2 times 2 times x minus a, which is 2c2 times x minus a, and so forth. And so now what we do is we say, okay, let's put x equals a in the derivative. Well, if we do that, then all of like this term here will equal 0 because a minus a is 0. This term here will equal 0. All the terms are equal 0 except the c1. So f prime of a equals c1. So now we know what coefficient c1 is. We have a formula for it. So far, are we okay? Are there any questions so far? Okay, okay. Well, then let us continue here. Hey, I'd like to know what C2 is. I'd like to know what C2 is, that coefficient. Okay, what do you think we're going to have to do to figure out C2? What might we have to do to figure out a formula for the second coefficient, C2? Well, but Josiah, something else. Look, for the first coefficient, we needed to take the first derivative. To get the second coefficient, we'll take, well, how about the second derivative? You're almost right, John. Second derivative. So look, I'm going to take the second derivative of my function, expand out what I have, and then I'm going to put x equals a back in. And then f double prime of a will equal 2 times C2. So therefore, C2 will equal f double prime of a all over 2. Okay? If we want to find C3, we'll take the third derivative. When you take the third derivative, you'll find that f triple prime of a equals 2 times c times C3, which is 3 factorial times C3. So C3 is equal to the third derivative of the function evaluated at a over 3 factorial. And incidentally, the second coefficient, C2, was f double prime of a over 2, but 2 is the same as 2 factorial. So in general, if there's a pattern here, and the pattern is that the nth coefficient of that power series, the formula to get the nth coefficient is to evaluate the nth derivative of the function at a and divide it by n factorial. And so by doing that, we get that if our function has this power series representation, the coefficients are given with this formula here. The coefficients are given with that formula. And so, given that, we can write out the power series for a general function. So long as the general function f is continuous and differentiable, we can get a power series. And the power series is f of a plus f prime of a over 1 factorial times x minus a plus f double prime of a over 2 factorial times x minus a squared plus f triple prime of a over 3 factorial times x minus a cubed, and so forth. That's called a Taylor series of the function f at a, or centered at a. Okay, is that? All right, are there any questions on this formula? How many think this is actually quite a lovely thing that you just saw here, how we developed this formula? Okay, thank you, Robin. I'm good. Thank you, Tyreek. Thank you, John. All right, good, good. It is absolutely beautiful. And a lot of times mathematics, thank you, Ryan, when mathematics is, when you get beautiful results, sometimes that helps you tell if the math is right. There was, I knew of an advisor in graduate school who, this is a story that I heard. He had a student who was talking to him about, he was a PhD student like me, and he was presenting this result to the professor. And the result was complicated and kind of ugly. And the professor said, I know that can't be right, your result, because it's not a beautiful result. And it's not an elegant result. And it turns out the professor was right. There was an error in the student's work. But when I think of the Taylor series, I always think of that story. Now, when A equals 0, the Taylor series, we call it a Maclaurin series. If you let A equal 0, Taylor series becomes what's called a Maclaurin series. Okay, so the x minus a's become x minus zeros in the Taylor series, and so you have just, x squared, and so forth. So, again, that like x there, that's like x minus 0. And x squared is x minus 0 squared. So the Taylor series is named after the English mathematician Brooke Taylor. He lived from 1685 to 1731. The Maclaurin series is named after Scottish mathematician Colin Maclaurin. I'm just looking at the little bibliography here. And he lived from 1698 to 1746. So these, mathematicians came up with these beautiful results in math because they needed to compute things. And if you have, just like you saw with the example we just looked at, if you have a definite integral that you need to compute and you can't get an antiderivative, how are you going to compute that definite integral? Well, one way is to find the power series for the function. So this is Taylor and Maclaurin series. And I want to get to a few examples, but are there any questions so far? All right, let's, while we're here, why don't we just look at this book example, something very simple. They want to find here in example 1, and this should be the same in your book. They want to find the Maclaurin series for the function f of x equals e to the x. So a Maclaurin series, well, okay, so here's the formula here for the Maclaurin series. So in order to get your terms of the series, you just follow the formula. So the first term of the series is f of 0. Well, what is f of 0? Well, what is e? Our function is e to the x. E to the 0th power equals 1. Okay? The next term is f prime of 0 over 1 factorial times x. Well, let's figure out what f prime of 0 is. Well, if our function is e to the x, f prime of x is e to the x, so f prime of 0 would be 1. Okay, so they don't show it, but there's a 1 x over 1 factorial. And in fact, all the derivatives of e to the x are e to the x. So when you evaluate those derivatives at 0, all the derivatives are going to equal 1. And so this is your Maclaurin series for e to the x. Okay, and if you want to find the radius or interval, if you want to find the interval of convergence, you just use the ratio test. So what you normally do is you enumerate the terms of your Maclaurin or Taylor series. You enumerate the terms, and then based on the terms, you figure out the formula. So in this problem, but that's normally how it works. But then, of course, you have your power series here, and if you want the interval of convergence, you just use the ratio test. And in this case, the series converges. Well, since the ratio is going to approach 0, the ratio test, the ratio of the n plus first term to the n term is equal to the absolute value of x over n plus 1. But as n gets large, for no matter what x is, as n gets large, that ratio approaches 0, and 0 is less than 1. So for all values of x, the series converges. And so that means r equals infinity. The interval of convergence is that x is between infinity and negative infinity. Okay, that's your interval of convergence, and therefore the radius of your interval of convergence is infinity. So this is standard. This is sort of standard to do this problem first when you just learn about Taylor and Maclaurin series. Are there any questions? Are there any questions at all? Okay, any questions at all before we move to the next example? Okay, all right, let's move to the next slide. So here, we want to find the Maclaurin series for this particular function, and also the interval of convergence. Okay, so all right, I'll let you copy this example here. Okay, so we want to find this interval of convergence. And I'm sorry, we want to find the Maclaurin series for the function. So in order to find a Maclaurin series, what must we compute for the function? what's necessary for a Maclaurin series? What must we compute for the function? Well, let's go back and look at the formula here. Okay. F is 0. That's right, John. What else? What else do we need if we look at the formula here? Let me bring up that Maclaurin series formula. Here it is. Of course, it's where A equals 0. Okay, there's F of 0. What else do we need to find? To find the series. Well, F is 0. F prime is 0. That's right, Robin. Derivatives. F prime is 0, very good. F prime is 0, F double prime is 0. So we need to find derivatives of this cosine function. Okay, so that's what we're going to do. That's what we're going to do. Let's move to the solution here. So what I've done is I have my function, and I find what f of 0 is for the function. My f of x is cosine of 3x over 4. So f of 0 can be shown to be 1/4. And then I'm going to compute f prime of x. And then I'm going to compute f prime of 0. And then I'm going to compute the second derivative of f. And then I'm going to compute f prime of 0. So in order to build up the series, I need to compute derivatives of the function at 0. All right, let me give you a moment to copy that. All right. Now, I have to take enough derivatives so that I can get a pattern, because I want to come up with hold on here, let me just check. I want to find the series, the Maclaurin. So I need the formula for the power series. But in order to get the formula, I have to take a few more derivatives. I need more information. So I'm going to compute the third derivative and the fourth derivative. What's one thing you might notice in the pattern about the derivatives? I mean, looking at these, looking at the values we're getting. What's something interesting about the derivatives? What can you tell me about the odd derivatives? The first derivative, the third derivative, fifth derivative, seventh derivative. What are all those and so forth? What are those all going to equal? They're going to equal 0. That's right, John. So, you know, that's an important observation. That's an important observation. So, okay, well, I went out 4 derivatives. Let me go now and based on the 4 derivatives, let me start constructing my Maclaurin series here. So I'm constructing the series. I'm constructing the series and trying to see if I can detect a pattern. And for this one, it even is helpful to maybe go out even to the 6th derivative. Okay, which I'll, and you'd have no problem computing the 6th derivative. The 6th derivative at 0, if you were to compute it, well, hold on. We know that the fifth derivative at 0 is going to equal 0. Okay, and the 6th derivative evaluated at 0. 6th derivative evaluated at 0. And I'm sorry, I wish it were a little neater. You'll find it to be equal to 729 over 4. And I actually show that on the next page. So let me just get to the next page here. What I do is I've expanded out. I've even gone out to the the 6th derivative terms, and I've written out the series. So I'm doing this again. You know, the book made, like, what I'm trying to do is really show the work very, very well out. Just like if I were a student. I mean, if this is new to you and you're trying to get the answer to this problem, this is what you would do, right? You would follow the formula very carefully. And that's what we're doing. We're following the formula very carefully. So the 5th derivative at 0 is 0, and the 6th derivative at 0 is 729 over 4. Are there any questions on this step here that I have, that I'm showing you here? And this is not one of the book examples. This is another example that I'm doing. I try to add to the examples in the book sometimes because it gives you more variety. Okay. So notice that we always have a 4 here in the denominator for our non-zero terms. There's always a 4 in the denominator. And then let's look at these numerators. We got 1, we got 9, well, we got negative 9, positive 81, negative 729. So the series is clearly an alternating series, but also you have, 1, 9, 81, 729. Gee, 1, 9, 81, 729. What's a common theme in that? I go from 1 to 9. I go from 9 to 81. I go from 81 to 729. What numbers involved in that? Right, 3, or even you could think 9. Both are correct. Both are correct. All right, so thank you. Thank you, John, Robin, and Josiah. So I'm hoping that based on the first 4 terms of the series, and I want to say the first 4 non-zero terms of the series, I can get the pattern. And this is where it's kind of like a little puzzle. You have to come up with a formula. You have to come up with a formula. So now notice here we have 2 factorial, 4 factorial, 6 factorial. So the 4, the 1 over 4 is just there, but we could insert a 0 factorial there if we wanted, because 0 factorial is equal to 1. So in the pattern in the denominator, I'm seeing 4 in the denominator, and I'm seeing even factorials. And so that leads me to believe then that in the denominator, I should have 4 times 2 times n quantity factorial. Just based on the behavior of the denominator. So you have to find enough terms in the Maclaurin series so you can understand the pattern. Are there any questions so far? Are there any questions so far? Okay, well, let's talk about the numerator. So the terms are alternating, positive, negative, positive, negative. So we'll have a negative 1 to the nth power to handle that. And then the powers are, well, 1/4 is the same as 1/4 times x to the 0th power. So we have an x to the 0th power, and then the next term has x squared. The third term has an x to the 4th. The 4th term has an x to the 6th. Okay, so x to the 0, x squared, x to the 4th, x to the 6th. Those appear to be even powers of x. Hence, I'll use x to the 2nth power. And then finally, we have 1, 9, 81, 729. So that could be thought of as 9 to the nth power, because 9 to the 0th power is 1. 9 to the first power is 9. 9 to the second power is 81. 9 to the third power is 729. However, if you have a problem where it's multiple choice, they may not have 9 to the nth power there, but they might have 3 to the 2nth power. Well, 3 to the 2nth power is the same as 9 to the nth power, because 3 to the 2nth power is equal to 3 squared raised to the nth power, and that's 9 to the nth power. Okay, so this is how you get a Maclaurin series. This is what you have to do. You have to take enough terms until you figure out the pattern. So for the exponential function e to the x, it was easy to get the pattern there. This one a little harder, which is why I wanted to do it with you. Okay, are there any questions before I move to the next page? Okay, so we're also asked in this problem about an interval of convergence, okay, for the Maclaurin series. What's the interval of convergence? Anytime you have a power series, you have to worry about its interval of convergence, because you're asking for what x values does our function equal the power series. It has to be for x values where the power series converges. So naturally, to find that, you're going to use the ratio test. So the nth term of the power series is equal to -1 to the nth power times 3 to the 2nth power times x to the 2nth power over 4 times quantity 2n factorial. Okay, so by the ratio test, you just take the ratio of the n plus first term to the nth term. And then you have to reduce this fraction, the ratio of these two fractions. So I'll take the top fraction and multiply by the reciprocal of the bottom fraction. Let me know if you have any questions. I'll give you a moment to copy it. Let me bring it down a little bit here. So, of course, the 2n plus 2 factorial, okay, we want to simplify that with 2n factorial. 2n plus 2 factorial is just 2n plus 2 times 2n plus 1 times 2n factorial. You know, 2n factorial would just be, you know, 2n, and you keep going down until you get to 3 times 2 times 1. But the fact is, the 2n factorials simplify out. I got to do this right. Sorry. I mean, hold on. The 2n factorials simplify out here and here, leaving you with, and the 4's simplify out, leaving you with hold on here. Do I have possible error here? Let me check something. One moment. I don't think this 4 should be here. That 4 right there, and I'm talking this part right here. I don't think that 4 should be there. Let me check. One moment. One moment here. Yeah, the 4 shouldn't be here. That 4 shouldn't be there. So now we take the limit of this as n goes to infinity, and no matter what x is, as the n increases, the denominator is going to infinity on our ratio. So no matter what x is, even if x is a billion, doesn't matter. As n goes to infinity, the denominator is going to get larger. And so the ratio is going to be less than, it's going to approach 0, which is always less than 1 as n goes to infinity. And therefore the power series, our Maclaurin series, is going to converge for all x values. Okay, it's going to converge for all x values. All right, and so the interval of convergence will be from negative infinity to infinity. Are there any questions on this part? Oh, okay, Josiah, what happened to the -1 in the last step? Good question. Well, we're taking the absolute value of this whole expression. So the -1 becomes a positive. 3 squared is positive, x squared is positive always, and the denominator is positive. Okay. Okay, thank you. Good question. Are there any other good questions? Okay, may I move to the next page? All right. All right. Well, all right. This means then that our interval of convergence is from negative infinity to infinity. So the radius of convergence is infinity. Okay. Now the book has some very good examples. They, for instance, show how to get the Maclaurin series for the sine and the cosine function. Okay, and they have good examples. So I'm trying to do some additional examples. So we did a Maclaurin series problem. Let's do a Taylor series one. All right, so I'm going to move to the next slide, if that's all right. Okay. All right, we're a little, so I do want to, this example, normally I like to have some time in class for classwork, but we're just going to have to utilize the time here that we have today because we are a little bit behind in the syllabus. So let's get this example done. And maybe, why don't we take a 5-minute break? I'll be right back and we'll get this example done. Well, we can all take a 5-minute break. I'll be right back. So I'll see you at 1:50. I feel like I should give you a little break here. See you at 1:50 p.m. and we'll finish this example. Okay, so we're back here. All right, we want to find the Taylor series for this function, which is equal to 1 over the square root of x, centered at a equals 9. Okay, centered at a equals 9. All right. All right. Hello, Dr. Carbone. Good to see you. We're just complete. We're going to finish out this little example here from section 0.7. And class, don't forget, Dr. Carbone, you have a study session tonight. Is that right, Dr. Carbone?
That's correct, at 8 o'clock. I'll be
Okay.
sending.
Great, great, excellent, excellent. All right, so, well, so if we go back here to our formula, this here, let me blow this up a little bit. This is the formula for the Maclaurin series. And what we have to do, see, we have to write out enough terms so we can detect a pattern. And then once we have the pattern, we can then write down what the power series is for our function. Now in this problem, we're not worried about, we're not worried about the interval convergence for this problem. I mean, what I mean is I'm not to say that you shouldn't always worry about it, but here we're just trying to get the right Taylor series formula. So, okay, we have to do the same thing we did for the previous problem. We have to do the same thing we did for the previous problem, and that's take derivatives. And so, and we're going to evaluate the function and its derivatives at a equals 9. So the previous problem with the Maclaurin series, we evaluated the function and its derivatives at a equals 0. But now we're going to evaluate at a equals 9. And incidentally, why do you think the value 9 is chosen? Why do you think a equals 9 is chosen? I mean, we're centering this Taylor series around a equals 9. Why might that have been chosen? You know, why not a equals 10? Why use a equals 9? Can anybody maybe offer a reason? You know, looking at the function, could anybody suggest a reason why a equals 9 is, you know, why we're centering that Taylor series around a equals 9? That's exactly right, Josiah. You have to take the square root. So the function itself has a square root of x in it. Well, the square root of 9 is 3. That's easy. And when you take derivatives of this function, you're going to always have square roots. Anytime you can, well, you can have different roots, but they'll involve square roots, and it's always easy. 9 is a nice value. So let's go ahead now. Very good. Let's go ahead and get to the solution. So here we go. I have my function. I have the first derivative and the second derivative computed. And then I'm evaluating the function and the first derivative and second derivative at a equals 9. So this one's a little bit harder than the last one, but it's still doable. And I'll tell you what, to not keep you in suspense here, let me show you that I'm doing a few more derivatives as well. And I'll let you copy this down. So I go out 4 derivatives. Okay. All right, so I'm just giving you a little time to copy all this down, and then I'm going to talk about, you might notice I'm rewriting the values of the derivatives. I'm rewriting them here. Reason for that. It's not. See, this function, 1 over the square root of x, we can never find a power series for that function using section 8.6 concepts. We have to use section 8.7. All right, so hopefully I trust we're okay on the derivatives. So in the derivatives, I'm choosing not to, like one, I have like the second derivative, I have 1 times 3 in the numerator. Third derivative, I have 1 times 3 times 5. Fourth derivative, 1 times 3 times 5 times 7. I'm choosing not to simplify that because I'm trying to determine a pattern. And I notice here that I have, 2 squared, 2 in the denominators, 2 squared, 2 cubed, 2 to the 4th. Okay. And let me just see here. One thing here, one moment. All right. So now, when I put in the 9, like for the first derivative, 9 to the negative 3 halves is the same as 1 over 27, which is, 1 over 27. But I write that as 1 over 3 cubed. Okay. 9, and then the second derivative, 9 to the negative 5 halves, is the same as 1 over 3 to the 5th power. Okay. 9 to the negative 7 halves on the third derivative is 1 over 3 to the 7th power. And then 9 to the negative halves on the fourth derivative is 1 over 3 to the 9th power. So what we're trying to do is we're trying to establish a pattern here. Are there any questions before I move to the next page? This is why I'm writing my derivatives in this way. And you know, all right, may I go to the next page? We're good? Okay. So now the Taylor series of our function centered at a equals 9, I'm going to write out the first 5 terms of the series. The 1/3 I'm going to leave separate. Now, I want to mention one thing, okay? I want to mention one thing. I believe in WebAssign this kind of problem, what they have is multiple choice. So like what I did in terms of writing out the derivatives, the factors, and so forth, it might not be obvious. So sometimes in WebAssign, what they do for harder kinds of problems is they'll give you a list of they'll have a multiple choice where they give you a list of choices, and then based on the choices, that can give you clues as to how you need to you write out your terms of the series so that you can figure out what the pattern is. I'm not thinking offhand that you would know to write the terms like I did just offhand. Now, for the problem we did before, where we found the Maclaurin series of the cosine of 3x over 4, that one you could just figure out the pattern and put it in a free response box, type in the formula. This one I think's maybe a little too hard for that, but at any rate, okay, so we have our terms of the series here, and a formula that will work is 1/3 plus this power series. Notice you have, in the terms of the series, you have x minus 9 to the first, x minus 9 to the second, x minus 9 to the third, and so forth. That's because we're expanding around a equals 9. If it were a equals 0, we would have x squared, x cubed, x fourth. But this is a equals 9. So that explains in the formula this part. And then, of course, you have 1 factorial, 2 factorial, 3 factorial, 4 factorial. That's there. You have 2 squared. You have 2 to the first, 2 squared, 2 to the third, 2 to the fourth. So that explains 2 to the nth power. And we're starting at n equals 1, by the way, here. N equals 0 won't work. You have to start at n equals 1. This alternates, goes negative, positive, negative, positive. So that gets the negative 1 to the nth power there. And then the factors, writing like this part here, like for the that term, you have 1 times 3 times 5 times 7. Well, if n is 4, you end at 7. 7 is 2 times 4 minus 1. Hence, you have 2n minus 1. The previous term, the third term, you ended at 5. Well, 5 is 2 times 3 minus 1. So that is the series. How many are thinking, man, this is a whole lot of math here? That's right. That's right, Robin. That's right, John. Well, you're now towards the end of the course, right? So you're getting ready to move into 200 level math classes, right? So, this is a gateway into those classes. This is a gateway into those classes. Dr. Carbone, I was telling the students how important these Taylor and Maclaurin series are for applications. Would you agree with that?
Oh, absolutely. Absolutely.
Comes up in physics?
All the time.
Okay. All right. So are there any questions at all? And Dr. Carbone, you know, is an expert on physics. So are there any questions on this problem? I know we're at the end of the class time here. All right, well, we'll stop the recording.